Hi everyone, I'd like to start this recording with something you've seen before, which is this wave on a string simulation. And I'm going to do it because it's going to serve as a mnemonic device. It's analogous to something that happens with thin film interference and light, but only analogous to. It's not the reason for it, and it doesn't explain how or why, but I guess it does explain how, but not why. But that's okay. It's going to serve as a mnemonic device. And what I'm driving at is this. When a wave travels through a string, if it hits a fixed, rigid object, something that's very hard to move, like this C-clamp here, well then, the wave gets to here and it pushes, if the wave is up, an upward orientation, the wave pushes up on the C-clamp, and the C-clamp thereby pushes down on the string and inverts the wave. It phase shifts the wave by 180 degrees. So please watch this. Let me slow it down here. This will slow down the wave for us. And so nice and slow, there it goes. And when it hits this thing, it'll push up on it, but that thing will not move. And the wave just got flipped, phase shifted 180 degrees. And same thing over here. But if this is a loose end, if it's easy to push up, right? And then the wave does not get flipped. It does not get phase shifted. So if this little ring is about the same density as the string, it's easy to move up and down, and the forces, the third law of forces, the reaction forces, don't flip the thing if it's easy to move. But if it's hard to move, or if it doesn't move, then it does phase shift it. The wave. It does phase shift the wave, right? So that's just something to help you remember. If a wave hits something that's hard to move, the wave gets phase shifted. If the wave hits something that's easy to move, then the wave does not get phase shifted. Okay, now that is just to help us remember something important, and that is this. When a light wave comes in, say light wave is incident. So here we have something on the left. This might be analogous or something. This might be a description of a soap bubble, right? Because a soap bubble is a really thin layer of water and soap molecules, a really thin layer of water and soap with air inside and air outside, and then that little bubble, that film itself is mostly water and some soap. So this would be N1, inside of there would be N2, and then inside of here would be N3. So, air, water, air. Now, I'm going to say to you, and this is going to sound familiar, that air is less optically dense than water. Water slows down light. Okay? So when light comes in, so here's an incident ray, the ray that gets reflected just hit something that's optically hard to move. And so this is where the analogy for the wave on a string comes into play. Right? It just hit something that's hard, it's more optically dense than the medium that it's in. And so, like a wave on a string hitting a C-clamp, this wave gets phase shifted. That is to say, if it happened to be sort of a crest of the electric portion of the wave here, well, then as soon as it hits this, that crest becomes a trough. So I'm going to say this. I'm going to say phase shift. And the answer is yes or no. And right there, the answer is yes. Okay? That wave gets phase shifted. This wave goes into the film, and there's a second wave that gets reflected off the film into the film. So the water-air interface here, but this is going from a more optically dense medium to a less optically dense medium. This medium, light travels through this medium more easily than it does through the water. So this wave here, that one there, does not get phase shifted. No. Okay, so a given wave of light comes in, like just consider some wavelength. 600 nanometer red light comes in, maybe 600 is orange, but I think it's red. And regardless, here comes some 600 nanometer light, and it gets phase shifted here. But it does not get phase shifted here. Now, what that means is if this N2 was really close to zero, If this N2 had a thickness really close to zero, right? If the thickness was basically, basically zero, or whatever, one layer of water molecules in thickness, right? Basically zero thickness. Then that wave got phase shifted, but that one did not. Those two waves got knocked out of phase, and you would have destructive interference because they're not in phase, right? Now, we haven't talked about the path length yet in this video, but I just want to talk about the phase shifting first, right? So in the event, if N2, if the thickness of N2, so the thickness of N2, if the thickness of N2 is approximately zero, very, very close to zero, then the top wave is phase shifted, the bottom wave is not, and you would get destructive interference, and you would not see the color, whatever I just said, 600 nanometers, right? Over here we have something different. Maybe this is, this might be, let's see, what? Air, water, and glass, right? So maybe this is a super thin piece of, what if we had here, so we have air, and we had a super thin layer of water, so N2, 1.33, and it's on top of a piece of glass, which is N3. Okay, so we have a ray of light that comes in, and it goes through the water, and then it goes into the glass, right? With some being reflected at each interface. Now check it out. Here, this wave is coming in. This light wave is coming in, and it hits the glass. It hits the water. It hits the water, and it goes from 1 to 1.33. It's harder to move through the 1.33. And so we do get a phase shift here. So the answer to the phase shift here is yes. Phase shift. Phase shift, yes. And then some of the light enters the water, and it bounces off the glass, and it comes out. And the question is it phase shifted? And the answer is yes, because 1.33 to 1.5 is sort of like, analogously anyway, going from a medium, it's like hitting something that's hard to move. It's like that wave on the string hitting the C-clamp. It's harder to move through the glass than through the water, and harder through the water than through the air. So we get a phase shift at the water-air interface, and we get a second phase shift at the water-glass interface, right? And so in the event that the thickness of the water in this case is about zero, very close to zero, so we don't have to talk about path length, right? If we've got a very, very, very thin layer of water, like again, one molecule thick of water, then the path length difference basically does not matter. But what does matter is they both got phase shifted, so they're in phase with each other. They both got flipped by 180. And so here you would have constructive interference due to the phase shifting. And here you'd have the other one, you had destructive interference due to the phase shifting alone. So that is of the utmost importance. You cannot solve these problems without knowing if there's a phase shift or not. Now, the other thing we have to know is this, that the wavelength in the medium changes because the velocity of a wave is wavelength times frequency. So, if the frequency stays the same, but the velocity goes down, well, these two numbers, obviously, the product of these two numbers equals the velocity. So if that goes down and that one stays the same, the wavelength inside the material must change. The wavelength inside of the more optically dense material, if V is going down, then wavelength goes down. And in fact, it can be shown quite readily that the wavelength in the material with an index of refraction of n is equal to the wavelength in a vacuum divided by n, the index of refraction. Okay, so that's how we can solve when we have to solve the wave. When we're dealing with path length in here, and we're talking about wavelengths and what happens with the waves, and they're flipping or they're not flipping, and they're whether or not they're going to interfere with each other. Well, when we're talking about the thickness of the material, we've got to be using the wavelength within the material to solve said thickness. Okay, so I think we'd be served well by looking at a couple of sample problems. So let's go to this one here. This is from oh no, it's not. This is from College Board. The next two are from Giancoli. All right, so the figure above shows white light in air. That means it's got all colors present with an index of refraction of 1. And the light strikes a thin film of oil, 1.8, that is coating a piece of glass, 1.5. A person looking down sees blue light of 425 nanometers coming from the location of the dot. The minimum possible thickness of the oil is most nearly, and it's a multiple choice question, so there's a few answers below, but let's just solve it first, okay? Now the first thing we have to do, let me just draw this quickly, or at least represent it, 1.8, and 1.5. So I'm going to draw a film. I've got 1.8, and 1.5. And let me write down some wavelengths. What do we have here? See, 425 nanometers coming from the location of the dot. So lambda as seen from above, we're seeing 425 nanometers. Light being strongly created, that is to say, undergoing constructive interference, right? So minimum possible thickness of the oil. Okay, so I have all the information here. Let me go back to my camera. Right, and so the first thing we do is, so N1 is 1, so this is the air, right? This is the oil, and this is the glass, I believe it was. Yeah, so a thin layer of oil on top of glass in an atmosphere of air. Okay, so some light comes in, and the first thing we're going to do is we're going to determine if there's a phase shift at each interface. So here comes some light, and that reflected ray, right there, that reflected ray, does it get phase shifted? It goes from somewhere that's easy to propagate through to somewhere that's more difficult to propagate through. And so it's like hitting the C-clamp. It's hard to move it. It's hard, you know, again, that's just an analogy, but it helps to remember. It's more a mnemonic device than really an analogy. But it helps to remember that, yes, there is a phase shift. So phase shift, yes. Just help keep our heads clear here. Then it goes through the oil, right? It goes through the oil, and some refracts into the glass, but some reflects off the oil-glass interface and comes back out, okay? And the question is here, is there a phase shift? Phase shift, question mark. From 1.8 to 1.5, no, there's no phase shift. This is hard, and it's going into a medium that's less optically dense. It's easier to get through here. This is sort of like that wave on the string just hitting a ring that's free to move, and it does not phase shift it. So phase shift here, no. Okay, so let me ask you this. In the event that, you know, this film of oil is super, super thin, like 1 molecule thick, basically with a thickness of 0, what would happen to these two waves? They would be knocked out of phase with each other, and there would be destructive interference, okay? Because they get knocked out of phase. This one gets phase shifted, but this one does not. Now, so there is a phase shift that happens on the top layer. There is no phase shift that happens at the bottom layer. And if the thickness was nearly 0, we would get destructive interference. So what are the conditions for this light to come out back in phase? Well, if there's no thickness, or essentially no thickness, they would be out of phase. So how do you put them back in phase? Well, you have a path length difference of a half of a lambda, half a wavelength, right? If this was a path length difference, and by path length difference I mean down and back up, because that's the total path that light goes through. Basically, you know, that much more distance. I'm drawing angles so we can see it, but these angles are super small generally. So we can just like look at the thickness, right, as a vertical distance. Right? So if it went one full wavelength down, one full wavelength total, that is to say half a wavelength down, half a wavelength up, then that would change nothing about their orientation with respect to each other, their phase with respect to each other, because they would still be out of phase. If they're out of phase when there's no path length difference due to the phase shifting, if there's no difference due to the if they're knocked out of phase due to the optical densities of the media, then
Sorry, I'm having.
That's Siri. We're not talking to you, Siri. Sorry about that, guys. let me start this. So this one gets phase shifted. This one does not. If the thin film was essentially zero, they'd be knocked out of phase because one wave that reflected ray got phase shifted and that one did not. They get knocked out of phase. Now, if the path length difference was a full lambda, they'd still be out of phase. Right? Just one wave back. But what if the total path length difference was a half a wavelength? Well, then they'd be put back into phase with each other, right? So here, right, the path length difference must be half a lambda. The path length difference must be lambda over 2. Which lambda? The lambda inside the material. So lambda sub n over 2. Well, that means the thickness of the film, right? If that whole path is half a lambda, then the film thickness is only a quarter lambda. So the thickness of this film must be the lambda in the film over 4. Okay, so how do we solve this? Well, I think we're just after the thickness of the film, right? So we're just after thickness of the film. And so the minimum thickness of this film for this to occur must be lambda sub n over 4. Well, lambda sub n is 425 over 1.8. Let me grab my calculator. 425 nanometers over 1.8 is 236.1. I'm just going to call it 236. So the wavelength in the material is 236 nanometers, okay, over 4. So the thickness of the film must be a quarter of 236, and 236 over 4 is 59 nanometers. The thickness of this film, at a minimum, is 59 nanometers. Okay, a little bit weird, but we'll do a couple more. We'll get used to it. Okay, next one. Let's see here. Okay, so let's take a look at this one here. If a soap bubble is 120 nanometers thick, what wavelength is most strongly reflected at the center of the outer surface when illuminated by white light? N is 1.32. So N is, water is 1.33. I guess this is soapy water. It's just a slightly under 1.33. So N equals 1.33. Air is N equals 1, and N equals 1. Okay, so let me switch to my camera. And oops, what we have here is this is the sort of cross-section of the soap bubble. Again, just to remind you, a soap bubble is a super thin layer, definitely not drawn to scale, of air, and then soapy water, and air. So air, soapy water, air. I'm just looking at like that right there. Okay, so I think, I forget the number I just read, 240? Sorry, no, 120 nanometers thick. Okay, so the thickness of this film, T, is 120 nanometers. Now what we have to do is this. First off, you've got to decide if there's phase shifts or not, right? And there are. There's a phase shift at first and not at second, right? So white light coming in that reflects off the surface does get phase shifted. Yes, to phase shift. But then the light gets refracted into the film and some reflects off that interface and comes back out and goes from water to air where it's easier to get through the air than the water. So this is slightly analogous to this wave on the string hitting the open ring that could just move freely. And so there's no phase shift here, no phase shift here. Okay, so in the event that there was no thickness, or very, 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 thickness approaching zero of the soap bubble, then these two waves I've drawn would be out of phase because there's a phase shift at the top but not at the bottom, and so they would get knocked out of phase. Now, we want to know what color would be most strongly reflected. That is to say, if you were this person right here watching, that's a person, that's their head, and that's their body. Right? If that's a person watching the light come off this interface, off this bubble, what do they see? Well, the light that travels an extra 240 nanometers, the light that travels an extra 240 nanometers does not get knocked out of phase. And so again, if the film thickness was 0, we could easily imagine that we'd see destructive interference here, and that this particular wavelength would be destructively would be not seen, would be destructively interfered. So what are the conditions to put them back in phase? Well, the path length difference must be half lambda to put them back in phase, right? And so the path length is 240 nanometers, 120 down, 120 up. So twice the thickness must be half the wavelength to knock them back in phase, right? So let's see what happens. Well, which lambda? Lambda n, of course, right? So what wavelength is most strongly reflected? Well, lambda will be multiplied by 2, 4 times the thickness, that's all. Right? Multiply both sides by 2, we get 4t equals lambda. So 4 times the thickness, and the thickness is right here. So 120, 240, 240, 240 twice. So lambda is 480 nanometers. That is the light that this person would see constructively interfere because of path length difference of 120 plus 240 nanometers is going to result in constructive interference at that wavelength because there's a phase shift that happened at the top but not at the bottom. So 480 nanometer light would be seen as a very strong emission by that person. Okay, one more, but there's a few parts to it. So let's go to a new. Right, I'm going to write this down here. What is the smallest thickness of the soap film? 1.33. So I'm going to quickly draw a soap film, and I'm going to write. So now we're n equals 1.33. That sounds familiar. That's the index of refraction of water. What is the smallest thickness of film? So we want the thickness that would appear black. Thickness for destructive interference. Okay, if illuminated with 480 nanometer light, T for destructive interference of 480 nanometer light. Oh, that's interesting. That's what we got with the previous question. Well, that was our answer. Assume there's air on both sides of the soap film. Yes. What are 2 other possible thicknesses? Okay, so 2 other thicknesses for the same thing. And if the thickness was much less than A, why would the film also appear black? Oh, let's do C first, because that's how we've been starting these. Okay, why? If the thickness was much less than A, why would the film appear black? Well, let's go to here. Okay, so again, it's a soap bubble, so it's N equals 1. Air, water, air. Inside of the bubble is also air, right? And so let's answer C first. If this was incredibly thin, approaching 0, this layer of soapy water, then what would happen? Well, this 480 nanometer light is coming in, and it reflects. Does it phase shift? The answer is yes. But does it phase shift here? And the answer is no. So no phase shift, and yes phase shift. That's the answer to C right there. If this was much, much thinner than, if this was approaching 0, then the 480 nanometer light coming in, hitting the upper surface, gets phase shifted, but the lower surface does not get phase shifted, so they get knocked out of phase by 180 degrees, and they would destructively interfere. So there's the answer to C right there, because the path length difference would have no effect if it's very, 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 very thin. Add a few more varies in there. Super thin, right? The phase shift would be what affects the constructive or destructive interference. In this case, it would be destructive interference if there was basically no thickness, or very, very thin, very small thickness. Okay, now what's the minimum thickness for destructive interference of 480 nanometer light? Well, it's near 0, but they mean the thin. If the film has a measurable thickness, what is that thickness? Well, they are knocked out of phase with each other by the indices of refraction, by the media that they're interacting with. They are knocked out of phase with each other just by that, right? So for destructive interference, we need them to stay out of phase, right? They have to stay out of phase. If they go half a wavelength total, if that one goes half a wavelength total, they'll be back in phase. So this must be a full wavelength, right? So twice the thickness must be lambda, right? So twice the thickness, right? That's the path length difference. The path length difference must be equal to lambda. What lambda? Not the lambda out here, the lambda in there. Lambda n. Okay? So twice the thickness is lambda n. So the thickness of the film must be lambda sub n over 2. Okay? So the thickness of the film is lambda sub n over 2, which is 480 nanometers, over, right, because lambda n is lambda in a vacuum over n, right? So 480 over 1.33, that's up there in the numerator, right? So that's the lambda in the new material, divided by 2. Okay, so let's just get that minimum thickness. We get 480 nanometers divided by 1.33. So in the thin film, this light has a wavelength of about 361 nanometers, and 361 over 2 is about 180.5, about 181. The thickness of that film must be 181 nanometers at a minimum, right? So minimum film thickness is 181 nanometers. That way they stay out of phase, right? Full wavelength, path length difference, they're still out of phase, which they got knocked out of phase by the media, right? So 181 nanometers. And then it says what are the two other thicknesses that would result in the same thing? Well, so it just, path length difference is 2 wavelengths or 3 wavelengths. That's all, right? So if you double that or triple that, those would be the answers, right? Because a path length difference of 2 full wavelengths, they're still going to be out of phase. And a path of any integer times wavelength. Maybe I shouldn't use n because we're using that for index of refraction. Any integer, I'll use a capital N. Any integer times the wavelength is going to keep this thing in the same orientation, right, as originally set up by the flipping flipping of the wave. Okay, so by the phase shift of the wave is really what I should say. So one full wavelength would keep them in phase. 2 full wavelengths, they'd still be in phase. 3 full, 4 full, 5 full wavelengths, they'll still be in phase. Any integer value times that wavelength of 161 or whatever that was, 361. Sorry. Any integer value times that wavelength is over 2 is going to give us that value. Is going to keep them out of phase with each other. Okay, so there's some thin films for you. It's a couple problems. All this being said, I've just been looking through the AP business, AP classroom, and there just aren't that many questions on thin films. But they do show up, so let's be prepared. And there you go. A lot to know. None of it's too complex. Just lots of steps, and do some practice, and you'll get better at this stuff and get familiar with it. Okay, talk to you soon. Bye-bye.